Hello, and thank you for joining us today for our seminar on software radio basics presented by Pentech. My name is Roger Hosking. Today we're going to cover several topics. First of all, complex signals, a very important concept for software radio. Then we'll cover digital downconverters, looking at receiver systems and decimation. And then we'll cover digital upconverters, looking at transmitter systems and interpolation. A real signal has one component, a real component, like this real waveform that we see here to the right. But a complex signal has two components, an I component, or in phase, or real part, and a Q component, or quadrature, or an imaginary part. And the Q component has a 90-degree phase shift relative to the I part. So here we can see a representation of the two components of a complex signal that are shifted in phase by 90 degrees. Complex signals can be a positive or a negative frequency. For positive frequencies, I leads Q, that is, the I component is leading or ahead of in phase of the Q component by 90 degrees. So you can see in these two waveforms that the I, which is the blue waveform, is ahead of the green Q waveform by 90 degrees. This is a positive frequency. For a negative frequency, the I component lags the Q, or is behind in phase by 90 degrees. So for these two waveforms, you can see the blue I component is behind the green Q component by 90 degrees, and so this is a negative frequency. In order to better understand complex signals, we're going to present another view to help make it clearer. Think of a rotating wheel centered on a horizontal real, or I axis, and a vertical imaginary Q axis. As the wheel rotates, a point on the edge of the wheel moves left and right along the I axis and up and down along the Q axis. If the wheel rotates at a constant speed, the values of I and Q are identical to the sine wave plots we looked at, 90 degrees out of phase. If the wheel rotates counterclockwise, we generate a positive frequency. So you can see the positive frequency waveform for a counterclockwise revolution. If the wheel rotates clockwise, we generate a negative frequency. So here we see a negative frequency complex signal where the I component lags the Q component by 90 degrees. You can think of a complex signal as a rotating vector with two components, I, which is equal to the cosine of the angle of the vector, and Q, which is equal to the sine of the angle of the vector, and with a positive or a negative rotation, corresponding to positive and negative frequencies. And the rotational speed of the vector is equal to the signal frequency. So there's one revolution of the vector per period of the sine wave that we're talking about. How do you make a complex signal? Well, one way is to multiply a real signal at frequency f1 by a complex sine wave signal generator at frequency f2. So let's start with a real signal at frequency f1 and send it into a complex mixer or multiplier, which has two multiplier blocks. We feed the lower inputs of each multiplier from the complex sine wave generator, first with the I component as the sine of the F2 frequency, and then the second multiplier with the Q component, or the cosine of the F2 frequency. Now if we go back to high school trigonometry, we have some trig identities. If you multiply the cosine of f1 by the sine of f2, which is what we do in the first multiplier, the identity shows 1/2 of the sine of the difference frequency plus the sine of the sum frequency. And in the second multiplier, if we multiply the cosine of F1 by the cosine of F2, we have a similar expression, but with a cosine of the difference frequency and a cosine of the sum frequency, that is the two frequencies. So if we simplify this formula a little bit by removing the higher frequency sum components, the plus components, we can reduce it to just these terms, and we can move those terms up in our block diagram, showing that in fact what we get at the output of this complex multiplier is an IQ term pair that represents the sine and the cosine, and it's the complex difference frequency signal that we've created. So the complex multiplication performs two operations. It translates the input signal F1 down to the difference frequency F1 minus F2. For example, suppose F1 was 90 megahertz, and that was your input real signal, and F2 was the local oscillator, and that was set to 70 megahertz. What you would get at the output would be a 20 megahertz complex frequency, 70 subtracted from 90. So that's the first thing that the complex mixer does, is it creates the difference frequency, but then it also converts the real input signal to the complex representation signal at the output. So translation and real to complex conversion. Those are the two things that this complex mixer does. Now let's take a look at the Nyquist theorem and complex signals. The Nyquist theorem states that the sampling rate must be at least twice the bandwidth of the signal. For real signals, we have one digital value per sample, represented by the vertical dashed line. However, for complex signals, we have two values per sample, the I and the Q. A complex signal sample contains twice the information as a real signal sample. As a result, the Nyquist theorem for complex sampling requires the sampling rate only to be at least equal to the bandwidth of the signal instead of twice the bandwidth of the signal. There's no free lunch here. It's just the same number of digital values. For each real sample, I get one value, and so I need to sample at twice the bandwidth. For each complex sample, I get two values, and so I need to only sample at a frequency equal to the bandwidth. Now let's take a look at digital downconverters. First, we take the antenna signal frequency as an analog RF signal and send it into an RF tuner, which downconverts the antenna signal frequency to an IF, or an intermediate frequency. Looking at the frequency domain view of this, we see the RF signal from the antenna shown over here at the right, and we have a signal band of interest that's defined by the two dashed lines. These are the frequencies that we're interested in, the band. An analog mixer inside the RF tuner translates the RF input signal down to an IF frequency, so that the resulting output of the mixer results in the lower image of the antenna signal frequency. In this case, if we had the RF signal at 90 megahertz and a local oscillator setting of 70 megahertz, we would have translated that 90 megahertz down to 20 megahertz. After the translation, we then need to filter the translated signal to pass only the signal bandwidth of interest. So in this case, we have a signal bandwidth that picks out a particular station, let's say, that filter eliminates all frequencies above and below the signal band of interest. So the station that we're tuning to is the only signal that gets through the narrow bandpass filter. But suppose we want to look at a different signal instead of the one we just looked at. Suppose we want to look at a different station or tune to a different radio source. The frequency translation, or the amount of frequency shift, is controlled by the setting of the local oscillator. So, if we want to change to a different station, what we need to do is we need to change the local oscillator frequency. We do this with a tuning knob. The tuning knob changes the frequency of the local oscillator, so that by changing the frequency, what we're effectively doing is shifting the translation of the RF signal so that a different signal appears at the IF frequency. This new signal then gets filtered by the bandpass filter so that only this signal now gets through the IF bandpass filter, and this is the station or the signal that we listen to instead of the previous one. This is the basic operation of a heterodyne receiver. Now, this bandwidth that we have may contain many different frequencies, and we use an A to D converter that digitizes the analog IF signal, producing real digital IF samples. Then we feed the real input into a complex digital mixer and local oscillator, like the one we looked at before. This will convert the IF signal down to a complex baseband signal. Over here at the right, we see an expanded view of that narrow IF bandwidth that we looked at before, and we can see that there are many signals within that bandwidth that we may wish to tune to. Perhaps this one. So the digital complex mixer now translates the desired specific input signal frequency that's within the IF band directly down to 0 Hertz, or DC, and it's translated down as a complex signal. So we use the digital mixer to translate this real input down to a complex baseband signal, and notice that the signal has energy above and below 0 Hertz. But because it's a complex signal, we preserve the negative and the positive frequencies that are centered at 0 Hertz and get a full representation of the signal that previously was centered at a higher IF frequency. Now we take the complex baseband translated signal output and use an FIR low-pass filter to limit the bandwidth of that signal. So here's our translated signal. We set a low-pass filter, a digital complex low-pass filter, to match the desired bandwidth of the received channel. So let's suppose that our channel bandwidth is this wide. In this case, the digital filter will remove all of the positive and the negative frequency energy outside of the bandwidth that we're interested in, leaving just the signal that we want. So now at the output of the low-pass filter, the complex baseband signal bandwidth has been reduced. We've reduced that bandwidth through the filtering process. The low-pass filter output signal is now decimated. Since the low-pass filter output is band limited, Nyquist tells us that we can lower the sample rate. Decimation means keeping 1 out of every n samples, throwing away the others. So here's the output of the FIR filter before the decimation, and the samples are coming out at the same rate as they went in, which is at the A to D sample rate, Fs. What decimation does is drops all but 1 of every n samples. So we can see here at the bottom the decimated filter output, and its sampling rate is now Fs divided by n, where n is called the decimation factor. It's the ratio of the input sample rate to the decimated output sample rate. If the decimated output sample rate is kept above the Nyquist limit, no information is lost. So we haven't lost any information in decimating if we follow the Nyquist rule. You might ask, why would we want to decimate? It's a major benefit. The same information can be processed easier in a DSP with decimated data because there are fewer samples to process. Remember, you're not losing any information, you're just delivering fewer samples per second. So a DSP will find it easier to do its signal processing job. You can also transmit the decimated signal at a much lower rate, use a cheaper channel, or get more channels in a particular channel bandwidth. Or, if you're recording, it'll require less memory to record the decimated signal than it would the non-decimated signal. So there are many system benefits in terms of making it easier for you to deal with the signal after it's been downconverted if you do the decimation. Taking a look at the operations that we've done so far with the complex mixer, the complex local oscillator, and the complex low-pass filter, collectively those three are called the DDC. Now the complex filtered digital baseband samples can then be sent over to the DSP or to storage or whatever for further processing, perhaps demodulation. In summary, digital downconversion is a two-step signal processing operation. In the first stage, we do frequency translation. The tuning, or the downconversion frequency, for the translation is controlled by the local oscillator setting. So we have a parameter of tuning frequency that controls the first stage translation. The second stage is low-pass filtering. Here, the decimation setting controls both the filter bandwidth and the decimation. As the filter bandwidth becomes lower, you can increase the decimation. So the one parameter, decimation, controls both bandwidth and the decimation factor because, in fact, they are proportional and track each other. So these are the two primary operations in a digital downconverter. Now let's take a look at digital upconverters. This is exactly the inverse signal processing scheme to digital downconverters, as you might have guessed. First, let's take a look at an overall block diagram of a typical software radio transmitter. In this case, we start with complex digital baseband samples at a sampling rate of fs over n, a low rate. We use a digital upconverter to translate these complex digital baseband samples to real IF samples, which are fed into a D-to-A converter that converts the digital IF samples to an analog IF signal. An RF upconverter then translates the analog IF signal to the analog RF, or the antenna frequencies. And typically a power amplifier boosts the signal energy so that it can be transmitted from the antenna. So now let's take a look at the critical part of this block diagram, the digital upconverter. First of all, the D-to-A output rate with real samples must be high enough to satisfy Nyquist. So we have to have a sampling rate that's high enough to support the IF output frequency. For example, if we had a 90 megahertz IF output, we'd probably need a sampling rate at least 200 megasamples per second. The digital mixer translates baseband samples up to the IF frequency, but the mixer must deliver output samples at the D-to-A sample rate, at fs. And the mixer is nothing more than a multiplier that generates one output sample for each of its two input samples. So the rate going into the mixer and the rate coming out of the mixer are equal to fs. They must be the same. So the local oscillator and the baseband sample rate must be at the D-to-A sample rate fs. The problem here is that the input digital baseband sample rate, which could be say a voice frequency signal sampled at a few kilohertz, is much lower. So how do we get from the much lower sampling rate of the input to the much higher sample rate that the mixer requires? Well, the answer is an interpolation filter. Let's take a look at that interpolation filter. The interpolation filter increases the sampling rate of the complex baseband input signal to match the required rate for the mixer. The interpolation factor n determines the ratio. So at the input we have complex samples coming in at Fs divided by n. At the output we have complex samples leaving at Fs. Here's a waveform representing the lower sampling rate baseband input, which is sampled at Fs over n. At the output of the interpolating filter, here's the same signal but sampled at a much higher rate Fs. Notice the waveform is exactly the same, and in fact interpolation does not change the baseband frequency. It just increases the sample rate. It's the same sine wave that we had at the input, but just with a much higher sampling rate, many more samples throughout the cycle of this waveform. So now the interpolated baseband sample rate matches the Fs sample rate required at the mixer input. The digital mixer then translates this complex baseband signal up to the IF frequency, using the complex mixer as an upconverter. So we start here with the complex interpolated baseband input that we just created in the interpolation filter, and we use the complex mixer setting the IF to the local oscillator frequency, so that if I want to translate that baseband signal to 90 megahertz, I set the local oscillator to 90 megahertz. And it translates the zero frequency, center frequency of the complex baseband input, and adds 90 megahertz to it, or translates it up in frequency. So again, the translated output appears at the IF frequency. Going back to the software radio transmitter block diagram just to review, again, the DSP, or the signal source, delivers complex digital baseband samples which are fed through the digital upconverter to produce digital IF samples, using the interpolation filter to boost the sampling rate up to Fs, and then the complex mixer and local oscillator to do the translation up to the IF frequency. The D to A converter produces an analog IF signal. It's upconverted further to the antenna frequency and then finally delivered out through the power amplifier to the antenna. So let's summarize the two operations for DDC and DUC. They're both two-step signal processors. The digital downconverter has two different processes. Translation is controlled by the local oscillator setting. And here there's one parameter that you set called the tuning frequency. As you tune the knob here, you get a different translation point. So this is one of the controls of the programmable parameters for a digital downconverter. The second parameter, as we recall, is the decimation setting, which controls the decimation and the bandwidth, controls both of them. And that sets the decimation factor n to control the bandwidth that comes out of the DDC and goes into the DSP. And simply by tuning the bandwidth knob, you can set different bandwidths for the filtering. These are two independent controls. You can change the tuning and the bandwidth independently to get the correct frequency and the correct bandwidth of the signal that you want to receive. The baseband sample rate, FB, which is at the right, is equal to the Fs, the A to D sample rate, divided by n, which is the decimation factor. And because the low-pass filter has an 80% passband characteristic, The baseband bandwidth is 80% of the FB, or the baseband sample rate. Now these two formulas are very key and very useful. We'll be using those as we go into more applications for software radio. Now let's take a look at digital upconversion. Again, it's a two-step signal processing task. We do the frequency translation the same way, again using a local oscillator and a digital mixer to translate the interpolated baseband signal up to the IF frequency, and to change the IF frequency, the translation frequency, we simply tune the local oscillator for a different frequency. And in order to feed the mixer with the correct sample rate signal, the interpolation filter controls the input bandwidth and the interpolation factor so that the sample rate of the input baseband signal is increased to match the requirements for the digital mixer. The formula that we apply here is the baseband bandwidth is equal to 80% of the baseband sample rate, and the output sample rate, Fs, is equal to the baseband sample rate times the interpolation factor, N. And again, these two formulas are essential for considerations in DUCS, or digital upconverters, in software radio applications. So let's just do a summary of what we've learned today. First of all, complex signals have two components, the I and the Q. Complex signals can represent positive and negative frequencies. And complex mixing translates a real signal and converts it to complex. In software radio systems, receiver systems use an analog RF front end to convert the RF antenna signal frequencies down to IF frequencies. Transmitter systems use an analog RF back end to convert IF signal frequencies up to the RF antenna signal output frequency. Pentec hardware interfaces A to Ds and D to As to these analog IF signals for both the transmit and the receive. In digital downconverters, we convert real IF samples down to complex digital baseband samples, and the tuning frequency determines the input signal frequency for downconversion. The decimating filter reduces the data rate for easier processing, storage, and so forth. In digital upconverters, we convert the complex digital baseband signals up to real IF samples. The interpolation filter boosts the baseband sampling rate to match the D to A and the mixer sampling rate. And the tuning frequency determines the IF output frequency at the D to A converter. So I hope this has been a useful presentation. It gives you the basic ideas and concepts that are throughout all of software radio systems. Thank you for joining us today.